Welcome. In this video I'm going to show you how you can analyze a single nominal variable using R and my own stikpetR library. I'm using Jupyter Lab with an R kernel, but this should also just work, or at least the code should also work in RStudio. To analyze a nominal variable, we can create a frequency table, then perhaps generate a bar chart from that. We could also determine the mode and the variation ratio, perform a statistical test like the Pearson chi-square goodness of fit test, determine an effect size measure for that, Kramer's V, perform a pairwise binomial test as a post hoc analysis, and then Cohen's G for that post hoc analysis. This video will mainly be about how you can generate the output, not so much on how you can interpret that output. Alternatives for visualizations will be available in the appendix. I'll leave a link to my website where you can download this Jupyter notebook. Alternative tests are available there, and also some alternative effect sizes. My library can be installed by using remotes, install GitHub, and then stikpet, and then stikpetR. It's not available on CRAN, so you can't just run install packages. You'll actually have to use this method or use the DevTools method. I'm not going to run this because I've already installed it once. Links in this notebook are actually to my Python library, but the function should behave in a similar or the same way. On my website you can also download a PDF for the R package as a manual. Alright, let's load in an example. And the data file also coming from my website, and then the one field, a nominal field. I'm using the marital status mar1, and that's the example. So you can see the first 5 responses there. Now the first thing to get an impression might be to use a frequency table. So I have a function for that which is known as tab frequency. It can't find it because I didn't import my library yet, so let's do that first. And now it should be able to generate a frequency table. It shows the frequencies, the percentages, the valid percentages. The difference is that these include the missing values, so these might not sum up to 100%, and the difference is those people who didn't give any of these as an option. We can then also visualize the result by generating a simple bar chart. I put height as percentages, and you nicely get a basic bar chart showing the same results. We can see that the peak is at married, which is also known as the mode, so you can use my mode measure function to actually also get that same result. Married is the mode. This will return multiple modes if there are 2 or more categories with the same maximum frequency. Unless all of them are equal. There are a lot of measures of variation for qualitative variation. I have one function that has about 20 of them. It's in the appendix below, but the variation ratio might be the most commonly one, so you might want to report that as well. Now, to test if these proportions or these counts are significantly different overall, we could use, for example, Pearson chi-square goodness of fit test. So I have test function Pearson goodness of fit, and that should give us all the results that we need. The sample size, the number of categories, the chi-square statistic, the degrees of freedom, the also important p-value or significance two-sided, the minimum expected count, the proportion below 5, and a description of the test that was used. There are a few additional settings here, but this gives you the basic Pearson chi-square test. The p-value is below 0.05, that's the usual threshold, so we therefore would reject the null hypothesis, and there are differences between the categories. As an effect size measure for this, we could use Kramer's V, but then specifically the one for goodness of fit. From the test results, I just grabbed the sample size, I grabbed the number of categories and the chi-square value, and then I can feed that into this function that should give me Kramer's V as an effect size measure. There are some rules of thumb for Cohen W, and why I'm mentioning that is because this Kramer's V can be converted to a Cohen W. So what we can use is the convert function from Kramer's v goodness of fit to Cohen W, and it needs one extra parameter, in this case k, for this conversion to work. So in this case that will result in 0.8022143. There's a rule of thumb for this, so we can use the th function and it will actually produce the classification and the source that was used for this classification. So overall, a large difference. Now, to pinpoint which categories are specifically significantly different, we could use a post hoc binomial test, and this will simply do all pairwise comparisons between any two categories. It shows you the sample size from each of those two categories. The observed proportion, so 44% was divorced compared to never married. We would expect 50%, so that these would all be each time 50%, because you're comparing these two categories. The p-value for that, and then adjusted with a Bonferroni correction. Now, if you want, you can also actually determine for each of these rows a effect size measure. So for example, Cohen's G. I have a separate video on how to analyze a single binary variable, because once you only have two, this actually becomes binary. But here's a bit of code that actually will add that Cohen's G for each of them. And here we can see all those classifications according to Cohen. As mentioned earlier, there are quite some alternatives. For visualizations, you could use a Pareto chart. There's a function for that. A pie chart, if you prefer that. Here's one. Then the dot plot, which the dot plot is actually not working, so that's why I cancelled it out, because it gives an error, so I don't like that. I might update that in the future. The Cleveland dot plot does work, however, which is actually a dot plot, but then only showing the top dot. Alternative measures, like I mentioned, for qualitative variation, QV, there are quite a lot of them. So here's a bit of code that has all the different options and then simply loops over all of them, and using that ME qualitative variation, and then shows you all the different options that are there. Alternative test, also quite a few. You could run a multinomial goodness of fit exact test. That takes quite a long time, so I'm only using the first 20 records in this case, just to show that it does work eventually. You could use a likelihood ratio test or a G-test, goodness of fit of course for all of these. There is the freeman-tukey version of that. There's the Niemann goodness of fit test. There's a mod-log likelihood goodness of fit test. There's a freeman-tukey-read goodness of fit test. And then there is power divergence, which includes, for example, Cressy-Read. It actually has an optional parameter lambda that you can put any value you like in. Alternative effect sizes could be that Cohen W itself. So there's a function for that. And of course we can then just apply that same Cohen W rule of thumb. JBME, so short for Johnson, Berry and Meekus E, also available. There's the function. It requires from our test results, and then that could depend on which test you actually used, but the sample size, the chi-square value and the minimum expected count. And the advantage is all of those functions for those different tests, they return those values for you, so you can just subtract the information that's needed. We can of course convert this again to a Cohen W, and that should give us again at 0.8022. Alright, this was in a nutshell how you can quickly analyze a single nominal variable using my library stikpetR. I hope this was helpful, and thank you for watching.